Example question from Newton's second law here. Remember from yesterday, Newton's second law says F is equal to m times a, right? The acceleration is directly related to the net force and is inversely related to the mass. We're going to use that here, but we're also going to use that in combination with some of the one or more of the equations that we learned in our last unit that involved acceleration. Let's write down some givens here first. We have a mass of a car of 1,000 kilograms. Something is 72 kilometers per hour. Tell me what that is. It is what? It is VI. Who said that? Good. It's VI. It's the initial velocity. Now, we're going to want to convert that to meters per second, right? We might as well do that now while we're thinking of it. How do you convert from kilometers per hour to meters per second? Multiply by 1,000 to get meters, so 72,000 meters divided by 3,600 seconds. So let's do that now. 72 times 1,000 on the top, divided by 3,600 on the bottom. That gives me meters, gives me seconds, which gives me, in the end, 20 meters per second. My time interval is 10 seconds. And I'm looking for the net force, right? F net. Sometimes, by the way, I just write F instead of F net. If I avoid a subscript like net, then I still mean the net force. Is there anything else that I have if I read between the lines here a little bit? Yeah? Yeah, the F is 0, right? It says what net force is required to stop the car. Stop the car. VF is 0 meters per second. All right. We know we want to use F is equal to m times a because we're looking for the net force. But I have a problem here. I don't know what a is, the acceleration. This is the only equation I have with force in it, so we know we're going to have to use this. We write it down. But let's find some other way of finding acceleration as well. Ideas? Yeah? Sure. We can say A is equal to delta V over delta T, or we can use any other group B equation because this problem involves acceleration. Delta V is VF minus VI, 0 minus 20. Over the time interval of 10 seconds, that gives me an acceleration of negative 2.0 meters per second squared. Be careful, it is negative. Why should it be negative, do you think? Yeah? Good. Yeah, good, Josh, because this car is slowing down, its acceleration would be negative. Now, the only way we'd make this positive would be if it was slowing down in the negative direction, so slowing down backwards, basically. But we're assuming it's moving in the positive direction. Slowing down gives it a negative acceleration. All right, now we multiply that by the mass. We get 1,000 kilograms times negative 2.0 meters per second squared, and we end up getting a value of negative 2,000. Agree? Josh, why is that a negative value? Yeah, like if a car is moving to the right, which way does the force have to be to stop it? To the left, opposite to the way it's moving. So if we make VI and VI positive, then the force needed to stop it has to be negative. It has to be opposite to the direction of motion of the car. Now, I told you guys on your first unit test significant figures wouldn't count, and I didn't take off marks for significant figures. Now I do. Now they count. How many digits should this answer be? How many digits is this? That's 4. Numbers at zeros at the end count as significant digits. So 1,000 is 4 digits. This is 2 digits. This is 2 digits. The final answer should be should agree with the least precise piece of data. So my final answer should be 2 digits. Now the only way to make 2,000 2 digits is to put it in scientific notation. So we're going to say negative 2.0. Negative 2.0 times 10 to the what? Times 10 to the 3. We know it's times 10 to the 3 because we're going from 1, 2, 3 decimal places. Negative 2.0 times 10 to the 3 dudes. If you said negative 2,000, okay, you'd get 3.5 out of 4. Okay, but if you want 4 to 4 now, you have to put in the correct number of digits. All right? I'll tell you that, especially on quizzes, feel free to get a little bit of help on significant figures now. I will mark you wrong if you don't do it right. But if you have a quick question about significant figures, like I won't answer like, if you say, how many digits should I round this to? I won't answer that. But if you ask me like, does this count as a digit or something like that, I will answer that for you on quizzes. I'll help you with that on quizzes just to get you kind of into that groove. So don't be afraid to ask the question. Okay, the worst that's going to happen is I say, I can't answer that. Hopefully within a few weeks it'll be all that and you won't have any trouble with it at all. Good? All right. Let's take a look now then at a specific type of force. One type of force that in combination with other things can contribute to the net force. Maybe you get 3 or 4 or 5 or 6 forces acting together to give you the net force, the total force. One of them could be friction. Friction is a resistive force. Do you know what I mean by that? Resistive force? It resists motion. Friction resists motion. When if I'm on a toboggan and I get to the bottom of a hill sliding on the hill and I'm moving to the south, then friction will resist that motion and eventually bring my toboggan to a stop. Friction resists motion. Okay, right now, okay, if I push on Jacob's desk, okay, there's friction acting on that desk as I give it a push that resists the motion of that desk. So friction is a resistive force, a force that resists motion. Now there's 2 kinds of friction. One's called static friction. Static means, don't even look at this definition yet. Static means what? Not moving. So static friction means not moving friction. It's the force of friction that prevents an object from beginning to move. This is not the toboggan sliding at the bottom of the hill coming to a stop. This is Jacob's desk sitting here having a force of friction trying to keep me from beginning to move it. I'm pushing the desk, right? But there's a force of friction that's trying to act against me to keep me from beginning to cause the desk to move. It's the force of friction that prevents an object from beginning to move. Whereas kinetic friction, the other kind of friction, is a force of friction that tries to slow it down once it's already moving. The force of static friction, this is weird. This is weird. The force of static friction changes. It varies. It's equal to however hard I push until it reaches a maximum value. I sometimes call the force of static friction the stubborn force. Stubborn force because it's just one of those pain-in-the-butt forces that just kind of tries to test you. I push with a force, it's like that pain-in-the-butt kid, right, that just pushes and pushes and pushes just as hard as he or she needs to push to get under your skin. Here's the force of static friction. Let's say the maximum force of static friction on Jacob's desk is 100. I mean, it could be 100, it could be 1,000, but let's say it's 100. The maximum is 100. I push on Jacob's desk with a force of 5 newtons. Desk doesn't move. Why? Because static friction pushed back with 5 newtons. I pushed on Jacob's desk with 20 newtons. Doesn't move. Why? Because friction pushed back with 20 newtons. It's a pain in the butt force. It pushes just as hard as I push, right? I push with 50 newtons. Jacob's desk doesn't move. Why? Because static friction pushes back with 50. I push with 90 newtons. Jacob's desk doesn't move. Why? Because static friction pushes back with 90. It just does whatever it needs to do to keep me from beginning to move this desk. Oh, but wait. I push with 101. What happens now? Desk starts moving. How come? Because static friction, that pain in the butt stubborn force, gave up at 100. The hardest static friction could push with is 100 in this particular example. If I push with 50, it pushes with 50. If I push with 90, it pushes with 90. If I push with 100, it pushes with 100, and nothing happens. But if I push with 101, static friction says, I give up. Throws its hands in the air, gives up, says, you win. Now I get to move the desk. Does that make sense? Now I'll tell you what happens at that point. When I move that desk, static friction doesn't just go back down to 90 or 80 or 70. Static friction becomes 0. 0. Then we've got another kind of friction that we'll talk about in just a second. Yeah, question, Jacob?
Do I add to the desk's friction?
Yes, you do. Jacob's question was, does he add to the desk's friction? He does, because the friction acting on the desk depends upon how hard the ground pushes up on the desk, and that depends upon how hard the desk pushes down on the ground. And if Jacob's sitting on the desk, that makes the desk effectively heavier, which makes that force of the desk pushing down more, which makes the force of the ground pushing up more, and that gives you a bigger force of friction. You'll see that when we give you an equation for friction, though, in just a few minutes. So static friction is that stubborn force. That pain in the butt force. That force that does whatever I do until it gives up, until I win. Right? Okay, Jacob is the force of static friction. He's that stubborn force. Okay? I push on Rachel's desk with a force of 20. How hard does Jacob push? With that little grin on his face, you know, right? Right? That stubborn static friction force. He's kind of just smiling, knowing that he's getting under my skin, pushing with the same force that I'm pushing with. I push with 80. How hard does Jacob push? 80. I push with 99. How hard does Jacob push? 99. I push with 100. How hard does Jacob push? 100. I push with 101. What does Jacob do? He says, see you later, I give up. The most I can do is 100. I quit. You win. Now we don't have static friction anymore. Jacob's given up. Yep. Now the other type of friction is called kinetic. Sometimes we call it dynamic friction. It's a force of friction that acts against an already moving object. That's the toboggan. The toboggan at the bottom of the hill is sliding, and it comes to a stop because of kinetic friction or dynamic friction. This is not an official name for it, but I sometimes call it sliding friction. Because that sometimes helps us to distinguish what kind of friction we have if we associate that word with it. Sliding friction. Now, kinetic friction can be a bit of a pain because it resists our motion, but it's not a stubborn force. If kinetic friction acting on my toboggan is 28 newtons to the left, then it's going to be 28 newtons to the left no matter what. If you've got a certain force of kinetic friction, that's what it is. It doesn't try to push harder or less, or it doesn't give you that little smirk, right? Push a little, just keep acting as hard as you're pushing, or acting as hard as you're acting till you overcome the maximum value. Okay, if the force of static friction is 20 newtons, that's what it's going to be. Or kinetic friction, that is 20 newtons, then that's what it's going to be. Now, this is important to explain a lot of things. The force of kinetic friction is usually lower, not necessarily than static friction, but it's lower than the maximum value of static friction. So, let's use Jacob's desk again for a minute as our example. We'll keep the maximum force of static friction on Jacob's desk as 100 newtons. I push on Jacob's desk with 20 newtons. What type of friction do I have? Well, what kind of friction is acting on the desk? Okay, I push on the desk with 20 newtons. Does it move? No. Then it's static friction, right, that's acting on the desk. And what's the value of static friction? 20 newtons. I push on it with 90. Does it move? Nope. Then it must be what kind of friction? Static friction. What's the value of static friction? 90. I push on it with 100. Does it move? Nope. What kind of friction is it? Static friction. What's the value of static friction? 100. I push on it with 102 newtons. Does it move? Yes. What's the value of static friction now? 0. Now we've got kinetic friction. And the value of kinetic friction we'll say is, don't know exactly, but we'll say 75 newtons. Okay, now listen carefully. I pushed with 100. It didn't move. Static friction must have been 100 to counter my applied force. I pushed with 102. Static friction says, give up. Kinetic takes over. Static friction is 0. Now kinetic is about, say, 75. I push on it with 200 newtons. Does it move?
Yes.
Yes. Kinetic friction. What's the force of kinetic friction? 75. I push on it with 1,000 newtons. Does it move? Yes. What kind of friction? Kinetic. What's the value of kinetic friction? 75. So static friction keeps doing what I'm doing until we reach that 100. Then it gives up and says, hey, kinetic friction, you take over. But when kinetic friction takes over, it's the same value always, no matter how much harder I push. So it's a pain because it resists our motion. But it's not a stubborn force in the sense that if it's 75 newtons, it's 75 newtons forever, no matter how hard I push. All right? Okay, here's a couple equations to describe this. We're going to say the static friction, the force of static friction, max, because remember, force of static friction is that stubborn force that like we don't really represent it usually by an equation. It's just however hard I'm pushing. If I push with 50, it pushes with 50. If I push with 80, it pushes with 80. If I push with 95, it pushes with 95. There's not an equation that describes that. But there is an equation that will get us the maximum possible value. Remember we said in Jacob's desk the maximum possible value of static friction was 100? We had to figure that out somehow, and that's with an equation. So that maximum possible force of static friction is equal to whatever that is. That's a Greek letter called mu. It looks like an M. It looks like a U. The Greeks called it mu. And it stands for something that we call the coefficient of static friction. And the coefficient of static friction has no units. It's just a number. It's a measure of essentially how much two things stick together. The bigger the number, the more they stick together. The coefficient of static friction between rubber and ice is about 0.2-ish. The coefficient of static friction between rubber and pavement is more like 0.9. Rubber and pavement stick together better than rubber and ice. So the coefficient of friction is just a measure of how much those two things stick together. Now, that force of static friction is mu times Fn. This stands for what we call the normal force. And that's measured in newtons. And the normal force is the force of the ground pushing up. Although I'm going to put the word up in quotation marks because it doesn't always actually push up. Not always, but we'll talk about that in a second. Usually the normal force pushes up. The ground pushes up. But if you're on the side of a hill, for instance, the ground pushes up and left. So it's not always up. But for now, let's just say it's the force of the ground pushing up. We'll deal with those other situations a little bit later. Force of the ground pushing up. And that is usually, not always, but usually the same as the force of gravity pushing down. In other words, you guys know what that symbol is? Therefore. Okay, usually it's the same as the force of gravity pushing down, so therefore the normal force will usually, not always, but usually be the same as m times g. What's g? 9.81. Mass times 9.81. For all the questions we're going to do over the next several days, it will be the same as gravity pushing down, m times 9.81. When we come across a situation where the normal force is not pushing up or is not m times 9.81, I'll let you know about that. I'll tell you that it's not the same as gravity, and I'll tell you why it's not the same as gravity. But for now, just assume that it is. This is a table of various coefficients of friction. What this shows is that there's varying numbers, like varying by quite a lot sometimes, that illustrate the coefficient of friction of different materials on different materials. If we have copper on copper, like, man, if you're trying to pull something on copper, well, you probably don't want to have it made out of copper, because the coefficient of friction between copper and copper is very, very high. Although you do notice the coefficient of static friction is higher, which means the maximum possible force of static friction is higher. But you can see it goes way down here like curling stone on ice. Like, there's hardly any friction of a curling stone on ice. If anybody ever curls, you know that throw a curling rock on ice, it just about goes forever almost, right? It's because there's almost zero friction on it. A rubber tire on dry pavement for kinetic friction is 0.8. On wet pavement, it's 0.5. How many people drive? If you drive, you probably recognize that wet pavement is harder to stop on than dry pavement because the coefficient of friction is lower. Therefore, the force of friction would be lower. How about this one? Anybody know what synovial fluid is? Yeah, it's what's in between your joints, exactly. Look at the coefficient of friction of synovial fluid on a joint. It's very, very low. That's a good thing, because if it wasn't very, very low, what's going to happen? You bend your elbow, and what's going to creak? You're going to hear this. You're going to feel this friction acting between your joints, which is not going to be very comfortable. That's arthritis, yeah. Yeah. No, I think that is what it is, yeah. All right. Let's take a look at this question. This says a sled with waxed hickory runners. So this would be like a, I don't know, like a sleigh that goes behind a horse or something. I don't know. Rests on dry, horizontal, dry snow. Calculate the mass of the sled if the maximum force that can be applied to the sled before it starts moving is 46 newtons. And we're going to use the table, right? The table on the previous page in order to get the coefficient of friction. But look at this question more carefully. Are we dealing with static or kinetic here? This is static. The maximum force before it starts moving is 45. What they're saying is this. You apply 35, what happens? Doesn't move. You apply 40, what happens? Doesn't move. You apply 45, what happens? Doesn't move. They're saying it takes 46 to get it moving. Right, Josh? 46 to get it moving. They're saying in this question, the maximum force of static friction is 46 newtons. Or it could be like 45.999, whatever. Right? It begins to move at 46. We'll say that's the maximum force of static friction. Doesn't mean that's what static friction is. If I push with 30, that's what static friction is. If I push with 40, that's what static friction is. This is the maximum force of static friction. Go back to Jacob's desk again for a second. Push with 80, that was static friction. Push with 90, that was static friction. Push with 101, now it's kinetic. The maximum was 100. The maximum force of static friction here is 46 newtons. We want to find the mass. So we're going to use our static friction equation. Our maximum force of static friction is equal to mu times the normal force. What do we say the normal force is, at least for now? What's it the same as? No. The normal force is the same as gravity for us for now, right? So we're going to say FSF max equal to mu times m times g. Right? Normal force just replaced with m times g. We're going to rearrange that to solve for mass. Take the mu and the g down by dividing. I get FSF max over mu times g. So FSF max is 46 newtons. Divide it by mu. Let's look at the table for that. Waxed hickory runners, dry snowy surface. Waxed hickory skis on dry snow, static friction, 0.06. Times 9.81. We do the math there, it works out to be 78.1515 kilograms. Can you understand here? We're not saying this is the force of static friction. We're saying this is the maximum force of static friction. The force of static friction could be 20 or 30 or 40 or 45. But it can be as much as 46 before it begins to move. Where would I round that to? Where would I round that to? How many digits is this? 2. How many is this? 3. How many is this? No. That's 1. The zeros after count. The zeros at the beginning don't count. That's actually only 1 digit. So we're going to round that to, what was it, 78.15? We've got to put that in scientific notation. We're going to round that to 8 times 10 to the 1 kilograms. Does that make sense? Right, you're looking at this first digit here. Okay, there's where you want to round it, but then you look at the number right afterwards, and it's an 8, so you have to round up. The 7 has to round up to an 8. And in scientific notation, it's just 8 times 10 to the 1. Here you go, page 185, 2 questions. I've put the table up here so that you don't have to keep referring back. If you want to work off a downloaded version of your textbook, you can get that table from the appendix, so you'd have to download the appendix. Might be easier just to snap a photo of it, though, to be honest, okay? Whatever you want to do, there it is. And you're going to need that in order to answer questions 1 and 2 on page 185. All right, first question says an applied force of 24 newtons forward causes a steel block to start moving. Let's assume that it just barely gets it moving. If it just barely gets it moving, then that means we've just barely exceeded the 100 Newton maximum force of static friction on Jacob's desk, right? Poor Jacob keeps having to move his desk back 20 times today. This is the maximum possible force of static friction. I've barely exceeded it. I've caused it to barely start moving. We know in question number 1 that I have FSF max. And its value is 24 newtons. I want to find the mass. This is similar to the example question. We're going to say FSF max is equal to mu times the normal force. But what's the normal force for us equal to? What's the normal force going to be equal to, usually at least? Mass times gravity, mass times 9.81. So we're going to say FSF max is equal to mu times m times g. And we're going to rearrange this to solve for mass. So it's FSF max, the maximum force of static friction, which we know, divided by, let's divide by mu times g. Okay, so let's figure this out. FSF max is 24. Mu between, what do we got here? Steel and horizontal greased steel. Steel block, horizontal greased steel. Steel on greased steel, static friction coefficient 0.15. So 24 divided by 0.15 times 9.81 gives me a value of 16 kilograms. Does that make sense? How many people got that? Good, good. Now let's take a look at question number 2. I'm going to slide this down actually so I got a little bit more room to work. Question number 2 here. This one says, suppose the sled in example 3.17 is resting on horizontal, wet, snowy surface. So for question number 2, we've got waxed hickory on wet snow. Waxed hickory on wet snow. The coefficient of static friction is 0.20. It says it's resting, so it's not moving. So the coefficient of static friction is what we want here. It's 0.20. What was the mass of it? I think 78 kilograms, something like that. 78.1515. Good. Let's find the maximum force of static friction. Was what? It's not. But wait a second, don't we already have the maximum force of static friction? No. This 125 doesn't tell us that's what it takes to get it moving. It's asking us that. Is 125 big enough? Okay, with Jacob's desk again, we had 100 newtons was the maximum force of static friction. Okay, if I said, hey, is 80 newtons big enough to get it moving? You would say, no, because it's not bigger than the maximum force of static friction. Is 125 newtons big enough to get it moving? I don't know. I need the maximum force of static friction to see if 125 is bigger than that. So let's get that now. FSF max is equal to mu times the normal force, which is, let's make some more space again here. Which is the same thing as saying mu times m times g. Mu, we said, was 0.20. 0.20 times 78.1515 times 9.81. Let's figure out what that is. Point 2 times 78.1515 times 9.81 gives me a value of 153. We would actually technically round that to how many digits? Bunch of digits, 3 digits, and 2 digits. Final answer should be 1.5 times 10 to the 2 newtons. Okay, so there's the maximum force of static friction. I apply a force of 125. Does it move? Does it move? No. I've got to exceed 150 to get it moving, and I only push it with 125. It's like at Jacob's desk. Okay, maximum force is 100. Push on it with 80. Doesn't move because I got to exceed 100 to get it moving. Does that make sense? Is this stuff making a little bit more sense than it was when you started these questions? Yeah? Go ahead.
Since an example.
Good question. The question was, if you didn't hear it, when we did the example, we rounded the answer for the mass to be 8 times 10 to the 1. So why didn't we use the 8 times 10 to the 1 there, the 1 digit there? Why are we using the unrounded number there? The reason is because we always, we round on a final answer. That 80 kilograms, or 8 times 10 to the 1, was a final answer. But now it's not again. Okay? Oh, if we're using that in another question, it's not a final answer anymore, so we have to use the unrounded number. Don't ever use a rounded number in another question. Always use the unrounded number in another question. Okay?